Welcome back to Integral Calculus. In this video, I want to talk about some properties of power series. And you can see on the screen behind me, I've got a list of some of the power series we have developed already in this course. We know the power series of the exponential function, the sine function, the reciprocal function, or at least this particular variant of the reciprocal function, and the natural log. We've derived these using the properties of power series. And now I want to see how we can use these to our advantage. Let me get my head out of the way, and the first thing that I want to mention is just that we can use these directly in order to derive new power series for transformations on our functions. So for example, if I have e to the 2x minus 3, well, all I've done is take this first series and replace x with 2x minus 3. So just replace x inside the series with 2x minus 3. And you have the power series for the new function. The second thing that I wanted to mention is that a power series is essentially a polynomial. And so the same rule for the distributive property should continue to work for all of these. So I have the expression for sine of x over there. If I want 5 times the sine of x, well, that would just be 5 times the series. K goes from 0 to infinity of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1 factorial. And we can bring that 5 inside the summation. So it becomes the sum. K goes from 0 to infinity of negative 1 to the k times 5 times x to the 2k plus 1 all over 2k plus 1 factorial. So we can very directly use skills in algebra in order to rewrite these summations and develop our new ones. Other thing that I want to mention is kind of related to that. We can classify power series as being like or unlike. There are two things that you want to look at. You want to look at the sum itself, and you want to look at the variable. In this particular case, for the sum on the left, I'm starting at k equals 0 and I go to infinity. For the sum on the right, I'm starting at k equals 1 instead. That means that these sums are not like. The other thing that you want to look at is the variable. The sum on the left, we have x to the k power. The sum on the right, we have x to the k minus 1 power. Again, these are not like. When the sums are not like, there's not a lot you can do. But you often, not always, but often can do a change in variables that will eliminate one of these problems. In this particular example, it would be really nice if this said x to the k instead of x to the k minus 1. So I might decide to let n equal k minus 1. Rearranging this, that means that n plus 1 is equal to k, and when k equals 1, n equals 0. That will allow me to change my k's everywhere they show up. It basically is a use substitution. It gets really messy when you do this because now your variables are going to be different. So I'm going to do a substitution over here as well, although this is going to be a really simple substitution. I'm just going to let n equal k. So the first sum stays the same, except instead of being for k, it's now for n. It goes from 0 to infinity of a n x to the n. My second sum is a little bit more involved. It started at k equals 1, and we said that when k is equal to 1, n is equal to 0. That's just plugging 1 in right here. So we now have the sum, n goes from 0 to infinity. We had bk, but we know that k is n plus 1. So this is going to be b n plus 1. We had x to the k minus 1, but we know that k minus 1 is n, so this is just going to be x to the n. And by doing this change in variables, this essentially use substitution, we now have the same summand in both of these, and we have the same variable factor in both of these. And now that we have it in that form, we can in fact combine like terms. This is going to be the sum, n goes from 0 to infinity, of an plus b n plus 1 x to the n. Related to that, let's look at one that actually has some numbers involved. Let's go, k goes from 0 to infinity of k x to the k. And let's go k equals 2 to infinity of x to the k over k minus 1. I think it's fairly obvious why I needed to start at something like k equals 2 for the second sum. If I had started at k equals 1, then I would have x over 0, which is undefined. And if I had started at k equals 0, well, then I'd have had to continue through to k equals 1, where it's undefined, and it would have been bad. But in this case, because the variable parts are the same, there's not really a change in variables that I can use. So instead, I'm going to look for the sum that has the smaller value of k, and I'm going to just start writing it out. If I plug in k equals 0, in this particular case, that's actually fairly boring. I get 0 times x to the 0, which is just 0. If I plug in k equals 1, I get 1 times x to the first, which is just x. And then I have everything else left. From 2 to infinity, and I can still leave that in the summation form. Now that I have done that, I've brought these two summations into a form where they can be combined. So my x in front will stay an x in front. My 0 in front is technically there, but adding 0 doesn't do anything, so I'm not going to bother writing it out. And then I have the sum, k goes from 2 to infinity. The first sum, my x to the k has a coefficient of k. The second sum, my x to the k has a coefficient of 1 over k minus 1. So I combine like terms by adding them together. The next rule is that integrals and summations behave nicely together. So I'll mention here that this only works when x is within the interval of convergence. This is true on all of the statements that we have done up to this point, but up until this point, the interval of convergence hasn't really changed too much. Or in other words, going back and finding the interval of convergence for the new sum would work nicely. For calculus, that's not always going to be the case. But if we have the integral of the sum, k goes from 0 to infinity, of ak x to the k dx, we can commute the integration and the summation. We can write this as the sum, k goes from 0 to infinity, of the integral ak x to the k dx. And that is going to open up some very interesting possibilities for us. I'm going to start somewhere that seems very innocuous. 1 over 1 minus x, which we know is the sum k goes from 0 to infinity of x to the k. I'm then going to look at 1 over 1 plus x squared, where I replaced, notice here this is a little bit tricky to see, I swapped x to minus x squared, because the minus turned into a plus, so it's minus minus x squared. So with that, I now have the sum, k goes from 0 to infinity, of minus x squared to the k. And I think it will be most useful to expand this out. Using properties of exponents, this is minus 1 to the k times x to the 2k. And now I'm going to integrate. The integral of dx over 1 plus x squared is the integral of the sum, k goes from 0 to infinity, of negative 1 to the k, x to the 2k, dx. And here I have to be a little bit careful, because my summation doesn't converge for all values of x. In fact, it converges for x in absolute value less than 1. So I should make a note of that. And that is true even under my transformation, right? When minus x squared in absolute value is less than 1, then x itself in absolute value is also less than 1. So haven't changed anything yet, but that might not hold true in the next couple of steps. Why am I doing all of this? Suddenly we have reached the point where some of it starts to make sense, because the integral dx over 1 plus x squared is arctangent of x. Well, I mean, I guess there's a plus c somewhere. I'm going to go ahead and put that plus c on the right-hand side instead of on the left-hand side. It'll make things a little bit easier in a future step. But I can bring that integral inside the summation as long as I'm assuming that x is less than 1. And I can bring that negative 1 to the k out, because as far as x is concerned, k is a constant. So I'm looking at the integral of x to the 2k dx. And that's a fairly easy integral to evaluate. Integral of x to the 2k is going to be x to the 2k plus 1 divided by 2k plus 1. And all of a sudden, we've derived a formula for arctangent. Although I guess we still have this c to worry about. To get there, I can just remind myself that the arctangent of 0 is equal to 0. If I plug x equals 0 into this summation, that all goes to 0, leaving me just with c. So I guess that c must be equal to 0. And arctangent of x is the sum k goes from 0 to infinity of negative 1 to the k, x to the 2k plus 1, all over 2k plus 1. We've now derived another power series representation of one of the elementary functions. I have one rule left. And if integrals behave nicely with power series, then it should make sense that derivatives do as well. And I'll look at this one in general because the derivative of x to the k is k times x to the k minus 1. Although you do have to be careful here because, well, we have this just factor of k that showed up here. And remember that when k is equal to 0, k is 0, and multiplying by 0 doesn't change anything. So very often you lose the lower limit of integration when you do this. Not always, but often. And that brings me to the problem I would like you to try. We need to round out our collection of elementary functions a power series for cosine. The classic way of deriving this is to use the power series of sine that I put at the beginning of this video, take its derivative, and you get the power series for cosine. It's not the only way to do it, but I think it's a very interesting way to do it, and I think it is within your wheelhouse at this point in the course. So take a couple of minutes and see if you can figure out step by step how to get the power series for cosine by taking the derivative of the power series for sine. See what you can do with that, and I'll see you in the next video.